When you're good, Jejun, we'll get started.
Yeah, I already
And I'll
started.
do intro. All right, great, thank you. All right, thank you all for coming to this week's Water, Climate, and Environment Seminar. We are pleased to introduce Dr. Bridget Scanlon, who is a senior research scientist at the Bureau of Economic Geology associated with UT Austin. She started here in 1987 and has since ascended the ranks and is a senior research scientist, and she also holds an adjunct faculty position at the University of Nebraska. A lot of her work is related to sustainable groundwater resources, and today you'll be getting some new insights from GRACE satellites on, I guess, water in some major US aquifers. So with that, let's welcome Bridget.
Thanks so much, Evan. I appreciate the opportunity to give this presentation today. And the title of the presentation is looking at the relative impacts of climate extremes and human water use from GRACE satellite data in major US aquifers. And this is a study that was funded by the USGS Powell Center with funding also from NSF. And I'd like to acknowledge other people working on this project, particularly Ashraf Rateb, who is a postdoc doing most of the data analysis, and Don Poole from the USGS, and Himanshu Save from Center for Space Research, David Weiss from JPL, and Alex Sun from the Bureau. Okay. So I'm going to try to address a few basic questions in the presentation today. GRACE satellites have been applied globally to evaluate water storage changes in river basins and aquifers, but the US provides a unique opportunity where we have a lot of groundwater monitoring and regional models that we can compare with the GRACE data. So we wanted to look at total water storage changes from GRACE and the major aquifers in the US and see if they're increasing or decreasing or remaining stable. And then trying to figure out what's causing those changes in water storage. Is it climate, or is it human water use, or is it both? And how are they interacting? And then to evaluate the reliability of the GRACE data, we compared GRACE groundwater storage changes with the groundwater level monitoring in these aquifers, and then also compare GRACE data with the results from regional and global models. And lastly, want to look at how we can use these data then to evaluate more sustainable water management practices based on our deeper understanding of these systems. So I'd like to provide some results from our studies and then going to the details of the analysis. So looking at water storage changes in US aquifers, what we find is that in most aquifers, in many aquifers, there was stored 15 years from 2002 through 2017. And declines in water storage have been limited to aquifers in the Southwest and South Central US. So that's mostly California Central Valley and Central and Southern High Plains. We found that the main cause of storage changes was climate, particularly drought in the Southwestern US. And these drought impacts were amplified by human water use for irrigation, switching from surface water to groundwater in California and Arizona and those regions. In contrast, in the Northwest US, conjunctively using surface water and groundwater mitigated the impacts of drought, and we see less drought in the north and east and the humid regions of the US. Then comparing GRACE data with other monitoring and modeling data to evaluate the reliability of the GRACE data, we generally found good correspondence between groundwater storage changes from GRACE and groundwater level monitoring data in the different aquifers. So it seems that GRACE tracks the water storage variability pretty well. comparing GRACE storage changes with regional models. We have limited time period and fewer models to compare with, but in most cases there was generally qualitative agreement. But in the Mississippi embayment, the GRACE data show very little storage change, whereas the regional model shows large declines in storage change over this 15-year period. Comparing with the global hydrologic models, which people look at a lot, PCR and water gap, we found that these models greatly overestimated groundwater storage declines in these aquifers that are heavily exploited, like the Central Valley and the High Plains. The land surface models that are developed by the climate community tend to correspond with GRACE better than the hydrologic models and follow the dynamics better, but then underestimate storage change in aquifers that are heavily exploited. And lastly, then, looking at these data, we feel that where possible, we should conjunctively use surface water and groundwater for more sustainable management. And in these situations, inefficient or flood irrigation with surface water helps recharge aquifers. And so this is almost like managed aquifer recharge or flood managed aquifer recharge. And then when you're using groundwater, it helps to use the most efficient system like drip systems to minimize storage depletion. If you don't have access to surface water like much of the High Plains, then you need to reduce irrigation pumpage to extend the lifespan of those aquifers. So, so that's sort of a brief overview of the study, because sometimes people get lost when I'm talking. So I try to kind of give the basic questions and the results, and then go into more detail. So I'd like to provide a little bit of background on GRACE and the modeling aspects, and then talk about the methods that we applied, and then go into the results, comparing GRACE total water storage and looking at the controls on water storage changes, and then evaluating the reliability of GRACE data. So most of you are familiar with the GRACE satellites, but the original mission was launched in 2002 and decommissioned in 2017, and the GRACE follow-on mission was launched a year later in May 2018. So it consists of 2 satellites that are about 450 kilometers above the land surface. So by measuring the distance between the satellites to micron scale resolution, then we get monthly variations in the Earth's gravity field that are controlled primarily by variations in water storage. So the GRACE data can be used to estimate changes in water storage from the land surface to the MOHO, and then we can look at the impacts of climate and human use on these storage changes. So I would like to show this NASA.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you've felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? More water, such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground. Knowing where the water and ice is moving helps us improve weather models, forecast droughts, floods, and wildfires. It also helps us get water where people need it. Measuring gravity from space helps NASA better understand the entire water cycle here on Earth. And that can come in handy next time you want a glass of the stuff. So
I think that kind of gives you an idea of what the GRACE satellites do. And this is a study that Matt Rodell and others published in 2018 in Nature, showing changes in water storage in system throughout the globe. And the blue areas are where we're seeing increases in storage, and this is 2002 through 2017. So you can see in the US, then let me see if I can get the pointer to work. So you can see in the US, in the northern region, we see storage increases. In the southern region, storage decreases that Matt attributes to drought. And in the Central Valley in California, groundwater depletion and drought. And you can see blue areas in different regions where it's been increasing, and red areas where it's been decreasing. And then Matt has tried to figure out what the causes of those changes have been over this time period. So we're going to focus on the US, where we've got a lot of ground-based data for comparison. So water storage changes reflect the balance between inputs and outputs. So it could be water supply versus demand. And these changes in storage can be related to changes in climate. As you saw from the video, droughts and floods, or human water use or groundwater pumpage. So once we see the changes, then we can try to determine what's controlling them. And the GRACE data tracks storage changes throughout the system. So it includes snow, surface water storage, soil moisture, and groundwater. So if we want to calculate groundwater storage from GRACE, then we have to subtract the other components like soil moisture we generally use land surface models, and surface water storage from reservoir monitoring, and snow from SNODAS. So many of you may be familiar with the major aquifers in the US, and you can see different types of aquifers throughout, different types of rocks. For example, in the Central Valley, in the north, the Sacramento Valley, in the south, the San Joaquin Tulare Basin. And it's a valley aquifer, so runoff from the adjacent mountains like the Sierras on the east and snowmelt from those regions feed into the aquifer. So although the Central Valley aquifer is only about 50,000 square kilometers, the contributing area is much larger, about 3 times this. The Columbia Plateau, basalt and sedimentary systems, and the Snake River Plain aquifer also similar. Upper Colorado, and the Arizona alluvial basin and range system, and then the high plains. So in contrast to a valley fill aquifer, the high plains is sort of isolated, and the most water input to the system is basically from rainfall on the system, very little input from river flows upstream. Edwards Trinity Plateau, carbonate system, Texas Gulf Coast and coastal lowland sedimentary systems, and Floridan carbonate and Pennsylvanian carbonate and karst. So groundwater storage, traditionally we've used groundwater levels to estimate changes in groundwater storage by multiplying by storage coefficient. And many of you are familiar with the detailed monitoring of groundwater levels in the High Plains aquifer by the different states. And generally the storage coefficient in the High Plains is often approximated to be 0.15 or 15% to calculate the groundwater storage. But in other systems where you have stacked aquifers, you can have shallow unconfined and deeper confined systems, and oftentimes it's not clear where the water level changes are occurring. So it can be difficult to estimate groundwater storage from point groundwater level data. But the GRACE satellites provide an alternative to estimate regional water storage over large areas with a minimum area of about 100,000 square kilometers. And for those of you that are more familiar with million acre feet, 100,000 square kilometer area. And so the High Plains, Arizona alluvial, Upper Colorado and Snake, these mostly behave as unconfined systems. The Columbia and Central Valley semi-confined, and all other aquifers we're looking at confined systems. So Lenny Konikow has done a lot of work on groundwater storage in the different aquifers throughout the US. And in a study that he published in 2013 for the, he shows changes in storage from 1900 through 2008. And cubic kilometers is approximately equal to million acre feet. 1.23 cubic kilometers is equal to 1 million acre foot. So you can see large storage changes in the Central Valley, in the Arizona alluvial system, in the High Plains system, throughout the High Plains system, and the Mississippi embayment. So these are areas where they've seen large declines in water storage, looking at the groundwater level data and looking at regional models. In the Northwest, then, Lenny shows increases in water storage in the Snake River Plain Aquifer, and also a slight increase in the Columbia Plateau Aquifer. And this is related to the use of surface water irrigation recharging groundwater. So at a regional scale, then, these are the trends in water storage, and much lower changes in storage along the coast here. So to provide a little bit of background on the global models, then, a lot of people look at global models and they like to see global maps of water storage changes. The two most widely used models are the Water Gap Global Hydrologic Model, WGHM, and PC Raster Global Balanced Model. So these were originally designed to estimate water scarcity, and they consist of a daily water balance, and they generally include the different component storages like surface water, soil moisture, and groundwater, and include human water use that they estimate with the algorithms that they developed to apply globally. The land surface models were generally developed by the climate community to provide the lower boundary condition for their climate models, and these are generally more physically based models and include an energy budget, but they exclude many of the component storages like surface water or groundwater storage, and don't route the surface water. In many cases, they're generally 1D models, and most of them do not include human water use or reservoir management. So let's look at the methods that we applied in the US then. So we looked at a GRACE total water storage anomaly. So we calculated the anomaly, because we were measuring changes in water storage, we calculated an anomaly over the time period, which is 2002 through 2017. We use a variety of different products, but the main products we use are University of Texas Center for Space Research MASCON solution and NASA JPL MASCON solution. And we include other solutions to estimate uncertainty in GRACE. So we looked at climate impacts on water storage by comparing the data with the precipitation and also with the US Drought Monitor, and looked at human water use impacts by focusing mostly on irrigation and the source of water for irrigation. And then we calculated groundwater storage anomaly for the various aquifers by subtracting snow, surface water storage, and soil moisture storage. Snow from SNODAS data, surface water from reservoirs, and soil moisture from land surface models. And then we compared with regional models, which are generally ModFlow groundwater models for the different aquifer systems, and we have data for about 7 systems. We also compared with composite groundwater level hydrographs for the different aquifers, with a total of about 23,000 wells, and we used the annual data for comparison. And then we compared with the global hydrologic models, PCR and Water Gap, and the land surface models, NOAA, CLSM, 2 different versions. So here you can see the regional models that we were able to compare with. So the Central Valley, the Columbia and Snake and Arizona, and the High Plains, Mississippi, and Gulf Coast regions. So let's look at the results from our studies then. So here you can see trends in total water storage over the 15-year period from 2002 through 2017. And the red reflects areas where the storage has been decreasing, and the blue is areas where it's increasing, and the yellow is within a plus or minus 5 cubic kilometers over the 15 years. So you can see many aquifers, there's very little change where we show it in yellow, and green and blue are where we see increases in storage in the north and east in the humid regions, and decreases in storage seem to be limited to the southwest and south central US. So over this 15-year period, we see about -9 cubic kilometer change in the Sacramento Basin in the north, and a -22 in the San Joaquin Tulare, -18 in the Arizona alluvium, -40 in the central and southern high plains, but an increase in storage in Nebraska in the northern high plains. -8 in the Edwards Trinity Plateau, -14 in the Gulf Coast, and -3 in the Mississippi embayment. Slight increases in these. The results for Florida are a little questionable from GRACE because you've got ocean surrounding it, and so that may impact the accuracy of the GRACE data. So do you think there's, unfortunately we're doing all of this in Zoom, so I can't ask you questions, but I mean, if you think back from the results from Lenny Konikow, what he was looking at from groundwater levels and regional models, where are the big changes, differences between what we're seeing from GRACE and what we see from his analysis? So if you keep this in mind, and then you look at Konikow's data, and we don't have the same time period, but if we look at his period from 2000 to 2008, you can see declines in storage in the Central Valley, a slight increase in Arizona, large decrease in the high plains. He also sees an increase in the northern high plains, which is detailed in his report, but in this map, he just shows the entire system as red. And then I think the biggest difference that we see is this huge decline in the Mississippi embayment from the regional model and from groundwater level monitoring data, whereas we see that in the Mississippi embayment, the storage changes are not that much, it's fairly stable. So who's right? Will we try to decipher that shortly? So now let's look at the time series of storage changes, and I'm showing one example here for the Sacramento Basin in the Central Valley, and the black line is total water storage changes, anomalies in millimeters, equivalent water height over time from 2002 through 2017. And so here you can see increases in storage around 2005, 2006, a decrease in storage in response to drought during this period, some recovery during the early 2010s, and then the long-term drought in California over this period. The gray bars on the background is the cumulative precipitation anomaly, where you can see increases in storage and decreases related to wet and dry climate cycles. And on the bottom then, you can see the results from the US Drought Monitor, and you can see the different levels of drought, with yellow being the lowest and dark red being exceptional drought. And so you can see very intense drought over this time period and a much less intense drought over this period. So I'm going to show these for the different basins around the US. So that's the Sacramento Basin that we just looked at in detail, and this is the San Joaquin Tulare Basin. So you can see 2007 to 2009 drought and a deeper decline in storage in the south with more intense drought. And I think what's extremely interesting here is that it looks like from the drought monitor that it ended overnight with an atmospheric river in January 2017. And so now people are looking at atmospheric rivers also in Texas because they may play an important role. So you need a big flood to end a drought. And that was a four-year drought, very extreme and but ended overnight then with floods. Arizona alluvial system, you can see, you know, a gradual decline in storage, and it seems to have been in drought over the entire period, but not as intense as the Central Valley. Central and Southern High Plains, then the drought in 2011, extending through 2014 and 15, and then a greater decrease in storage during this drought period from Grace. The Northern High Plains, then you can see a decrease in storage initially in Nebraska, then an increase in storage during a wet period, and then the 2012 drought, flash drought, and then recovery. So overall increase in trend in storage and less extensive drought from the drought monitor relative to the Central and Southern High Plains. In the Northwest, you can see in the Columbia, drought is not as intense as we see in other regions, and we don't really see very good correspondence between water storage and drought. Similarly, for the Snake, there seems to be a disconnect between total water storage and drought conditions. The Upper Colorado, same situation. And then in the humid region in the eastern US, you can see very little drought generally, and water storage changes slightly increasing or fairly stable. Also in the Mississippi embayment, which the regional studies were suggesting large declines. And then in Edwards Trinity, you can see a large decline in storage here related to the drought, and similarly in the Texas Gulf Coast, smaller storage change. So we generally see a good correspondence between the droughts and water storage changes, except in the Northwest, particularly in the Snake and Upper Colorado, those regions. And we can provide a single number for these droughts, the Cumulative Drought Severity and Coverage Index, which is available on the US Drought Monitor. So it basically captures that time series in a single number, and you can see that these cumulative drought indices are lower in the east and southeast, where there's less drought, and higher in the southwest, Central Valley, Arizona, and those regions, Central and Southern High Plains, then in the northwest. So next, so we've been looking at the relationship between water storage changes and drought. Next, I want to look at land use and human water use, and here show the irrigation, distribution of irrigation and cropland and other water use, land use in the US. And the blue shows the irrigated areas, very intense irrigation, Central Valley, along the Snake River, northwest part of the Columbia, and then throughout the High Plains, and the Mississippi embayment. So these are very intensely irrigated areas. So how does the water storage trends compare with the water use? So here I show human water use, and I'm showing data for 2010 and 2015 as examples. And the light blue at the top is surface water irrigation, the dark blue is groundwater irrigation, and the gray is other water use. So you can see in the Columbia overall, and it's cubic kilometers per year, which is similar to million acre feet per year. And for context, Texas used about 14 million acre feet in 2017. So you can see the Columbia doesn't use very much water for irrigation relative to the Snake, but they use a lot of surface water in the Snake River Plain and less groundwater. So that inefficient flood irrigation recharges the groundwater in those systems. In the Central Valley, you can see that 2010 was a wet year and 2015 was towards the end of the extreme drought. So during the wet periods in the Central Valley, San Joaquin and Sacramento, they use a lot of surface water irrigation, about 70% surface water. But in 2015, during the drought, the total water use didn't increase, so water demand did not increase. But you have a switch of the sources from to 70% groundwater during drought and about 30% surface water. So you're taking water from storage, from groundwater during drought, and you're also losing out on that recharge that you get from using surface water irrigation. And in Arizona, then about equal amounts of surface water and groundwater. In the earlier period, before about 2000, they used predominantly groundwater, had large groundwater level declines, but then they created the Central Arizona Project to transport water from the Colorado River to the irrigated areas. And then that decreased the depletion a lot and decreased the subsidence and helped with recovery. In the upper Colorado, it's mostly surface water. So when people say, some people in the past have said the depletion and storage is attributed to groundwater use, it's important to look at to determine whether they are using groundwater or not. And it seems like in the upper Colorado, they're not. In the northern high plains, they're using some surface water from the Platte River, but mostly groundwater. And in the central and southern high plains, it's nearly all groundwater because there's no surface water. Irrigation in the Edwards Trinity Plateau is very small, so the storage changes that we're seeing here then are mostly related to climate. And in the Gulf Coast, then some irrigation, surface water, and groundwater. So the Mississippi embayment, you can see that groundwater irrigation is greater than that in the Southern Central Valley, which is sort of amazing. And they use some surface water, but it's mostly groundwater. So it's interesting, why don't we see a lot of depletion in the Mississippi embayment when we see that they're using so much groundwater? That's something you can think about. And then very little irrigation in the eastern humid regions. So we looked at the trends in total water storage, seeing depletion in the southwest and south central US and stable or rising trends in much of the other regions. It seems like a drought is very important, particularly in the southwest and south central regions, and very little drought in the humid eastern regions. Water use also is very important and can amplify or dampen the climate impacts. So in California and the Central Valley, when we switch from surface water to groundwater, we're amplifying the impacts of drought on water storage change and causing greater changes in storage. In the Northwest, when they use surface water, they're dampening the impacts of climate. And that's why in the Snake, we didn't see a good connection between water storage and climate. In Nebraska, where you saw that there was an increase in storage, some of that is related to surface water use, and which helps. So now let's look at comparing Grace water storage change with groundwater level data and with models. So here I'm showing Grace groundwater storage, Grace total water storage change in the black line, and this is for the San Joaquin Tulare, the southern part of the Central Valley, and the blue then is the line after subtracting surface water reservoir storage, soil moisture, and so you can see a much more damped water storage trends in the groundwater in this region. And then if we look at all of the aquifers, then in general, you see pretty good this is the San Joaquin Tulare, where you see the more damped impact on groundwater. But many of these basins, the groundwater storage seems to track the total water storage. And there is, soil moisture storage does not seem to play a huge role in impacting the total water storage. So for example, in the northern high plains, we're using soil moisture storage from land surface models, so that could impact these results. But in general, the trends in groundwater storage are very similar to those from total water storage that we just discussed. So if we look at the groundwater level monitoring data, so we're looking at groundwater levels in the winter period and comparing that with groundwater storage from GRACE. And so you can see generally good qualitative agreement between the two in these different systems. And high correlations, you know, for example, central and southern high plains almost 0.9, correlation coefficient of about 0.9, but not in some other regions. So here, poor correlation in the upper Colorado, where the storage changes are low. So in general, I think GRACE is tracking the dynamics of groundwater storage changes and from these data. So I think the aquifer that we have learned the most about groundwater level data is the high plains, and Ginny McGuire has been monitoring groundwater, has been collating the data from the states to provide these maps of groundwater storage changes. And so you can see her map from 1950 to 2015 shows increases in groundwater levels in the Nebraska region and large decreases, particularly in the northern part of the Texas and also in Kansas. And this is partly related to recharge in the sandhills because of the coarse texture, a lot of in the sandhills region, and also use of surface water from the Platte River recharging the groundwater. And you have much finer textured soils, Pullman clay loam and other soils further south that are limiting recharge in those regions. So then comparing GRACE groundwater storage with regional models. So this is the Central Valley model that Claudia Font developed and is updating. So you can see generally good qualitative agreement between GRACE groundwater storage and the Central Valley model. The northern high plains, we have a very limited overlap period, but again, qualitative agreement. The southern high plains, the GRACE is the black line, and you can see that it's showing more dynamics. There was a wet period about 2006, 2005, 2006, and the regional model in blue does not seem to pick that up. So maybe recharge in the regional model that Interra developed may not be as dynamic as it actually happens. And the biggest discrepancy between GRACE and regional models is for the Mississippi embayment regional aquifer system. So huge decline in storage from the regional model, and GRACE just suggesting that there's very little storage change. So either GRACE is wrong or the model is wrong. And so the USGS is doing a lot of new work to look at the connectivity between the Mississippi aquifer and the groundwater system. And maybe they're underestimating capture of surface water. So even though you're pumping a lot of water from the groundwater, it may be capturing surface water from the streams. And the grid scale in the model may not be high enough resolution to also capture the, to show the stream capture. So we feel like maybe the regional model is overestimating groundwater storage change, and really a lot of that pumpage may be derived from surface water. So these are long-term regional models, which are a fantastic resource. And you can see some of these developed back to the 1930s. And you can see the Columbia Plateau showed increases in storage in the 50s and early 60s in response to surface water irrigation, and then fairly stable or up and down since that time. The Central Valley since 63, you can see each of the droughts and some recovery in between, but this drought from 87 to 92, a large decline in storage, and the recoveries are not enough. So there's a net decline in storage in the Central Valley. And this is the regional model of the Mississippi showing from about 1980, large declines in storage, but they're questioning those at this time. The Southern High Plains, this is the Interra model showing large declines in storage, from about 1950 because they don't have any surface water to help with irrigation. So now I'd just like to do a very brief comparison between GRACE and the global models, because you see so many papers these days on the global models. And so here I'm showing an example for the Southern Central Valley, San Joaquin Tulare Basin. The GRACE data are shown in black, and this is groundwater storage anomaly in millimeters. And the blue is the water gap, global hydrologic model, and the orange is PCR. And the green is the ensemble from the land surface models. So for this particular basin, you can see that the land surface models seem to track GRACE better than the global hydrologic models, but that may not be for the right reason. I mean, I think maybe they're getting the climate correctly, but they don't have human water use included. But the global models seem to overestimate human water use, and in this particular basin, particularly PCR, global water balance. So large discrepancies between the global models and GRACE. And so if we look at the different basins, there's very little change in the northern basins. And so we're not seeing much change in the global models. But as we just showed for the San Joaquin Tulare, these global hydrologic models that include human water use seem to be overestimating groundwater depletion in those basins. Also in the Arizona alluvial basin, these global models are overestimating. And the central and southern high plains, and also in the northern high plains, they're just not tracking what's happening, but the land surface models seem to do a better job. And again, here, we're not seeing the decline in storage in any of these global models that we see from GRACE. And you can see the Mississippi embayment water gap shows a huge decline in storage, and the other models are fairly flat. So they don't really seem to do a great job of tracking water storage changes. So it's important to evaluate these global models in areas where we have a lot of other data, and the US is certainly a place where we have that. This is the study that Petrodol with water gap model published in 2012. And I think it's really nice because the blue areas are showing a negative net abstraction. So it's basically showing where surface water irrigation is recharging groundwater. And so we can see that in the northwestern US and in many other regions globally. So the value of surface water to recharge groundwater. And that conjunctive use of surface water and groundwater. So lastly, I want to just talk briefly about how can we manage water resources more sustainably. The approaches will differ by aquifer system. So in the Central Valley, you know, the surface water and groundwater are connected, and they conjunctively use both. And if they use inefficient surface water irrigation or flood irrigation and efficient groundwater irrigation or drip systems. And more recently, you know, they're using flood irrigation in the winter when the crops are fallowed to increase recharge to these depleted aquifers. So I think that makes perfect sense and will help. And with the Sustainable Groundwater Management Act, I think they'll have to do more and more of this. The Arizona alluvial basin is also conjunctively using surface water and groundwater and managed aquifer recharge with recharge basins. But with drought conditions, then their allocation from the Colorado is going to decrease a lot. And so they're now paying some of these groundwater management areas to install wells so that they will be able to pump groundwater again. And so we may see depletion and subsidence again if they don't have access to surface water from the Colorado. Central and southern high plains, most of these systems, the groundwater and surface water is disconnected. So we really need to use very efficient irrigation systems, which they are using, and deficit irrigation to extend the lifespan of these aquifers. The northern high plains, they're conjunctively using the plat and the groundwater, and then a little bit of managed aquifer recharge up the irrigation canals. to promote recharge through these unlined canals. Columbia and Snake, we had to talk recently from people at the Snake River Plain where they're using managed aquifer recharge and taking up to half a cubic kilometer from the Snake River and applying it in spreading basins and stuff to recharge. They have the advantage of having an irrigation system to do that. Mississippi embayment, I think even though they're pumping a lot of groundwater, that it's really capturing surface water from the streams, and now they're moving in the direction of doing more managed aquifer recharge also. And Texas aquifers, you know, I think there's a lot of impetus then to increase managed aquifer recharge or aquifer storage and recovery in different regions, and HDR and the Bureau are doing a study at the moment, and I think we'll see more and more of that. So managing droughts and floods, Chen Yang in our group did a study on the left-hand side here, the data from the water data from Texas, which is the best thing since sliced bread. You can see reservoir storage currently 43 cubic kilometers and 82% of capacity. And you can see in all of these blue areas, then if you could take some of that surface water and put it in the depleted aquifers, like the Trinity Aquifer or the Houston area groundwater, you know, it would help with the sustainability. So Chen showed that if we could capture greater than the 95th percentile flows, we would that would account for 37 cubic kilometers over a 3-year wet period, 2015 through 2017. And that's equivalent to twice the water use in Texas in 2016. But that's not saying there are, of course, huge logistical issues, but it wouldn't impact the water rights, and in most cases wouldn't impact in-stream flows, but much more detailed studies would need to be done to evaluate that. And this is the study that I mentioned in the Snake River Plain, where they've been taking water from the Snake River and putting it in aquifers up to 500,000 acre feet in 2017, 2018. Very successful program to recharge the aquifers. So to summarize then, you know, a lot of emphasis on groundwater depletion, but I think in the US, most of the depletion is in the southwest and south central US. Many other regions, it's fairly stable or rising at the regional scale, but could be locally declining. The causes, climate plays a big impact on storage changes, particularly droughts, but then human intervention can amplify or dampen those impacts. Amplify by increasing groundwater pumpage during drought, and dampen by having conjunctive use of surface water and groundwater, as we saw in the Northwest. Generally good qualitative agreement between GRACE groundwater storage changes and groundwater level monitoring data. We generally think of regional groundwater models as probably being much more accurate than other models, but I think the large discrepancy between GRACE and the Mississippi embayment questions the reliability of this model, and USGS is currently doing a number of studies to evaluate that and test different things. But GRACE suggests very little storage change, and whereas the regional models suggest large declines. The global models that include human intervention use global algorithms to determine the source of water and the magnitude, and they tend to overestimate groundwater depletion in the heavily exploited aquifers in the US. And then, as we just talked about, conjunctively using surface water and groundwater is extremely important. Managed aquifer recharge, which we call now, but in the past, inefficient surface water irrigation combined with efficient groundwater irrigation. So this was part of a Powell research group, and once in a blue moon, you're allowed to have fun and enjoy yourself. So this was one of our meetings in Colorado, and many of the people in the team. So very grateful to the Powell Center and to National Science Foundation, and also to the Jackson Endowment and Fisher Endowed Chair to have time to do this study. I would be glad to answer any questions.
Thanks, Dr. Scanlon, for an awesome talk. Do we have any questions from the audience?
Hi, this is Geeta Prasad. I'll jump in with a question. Thanks for that great talk, Bridget. So I don't think we have the chance to meet yet. I'm a new faculty in the Jackson School in the Department of Geological Sciences doing climate modeling, and I was struck by some of the comparisons between the land models and the GCMs and versus the GRACE data. And I was curious if you could comment, sort of based on your study, what is the duration of drought or water deficit that is necessary to see a signal in the groundwater measurements, and how much of that, the lack of variability that we're seeing in the land models compared to the GRACE data is likely to come from underestimating climate variability overall versus underestimating communication between water at the surface and the groundwater.
I think nice to meet you through Zoom, Geeta, and welcome to Austin. I think the land surface models have a number of limitations. They are missing surface water storage, they're missing surface water routing, and so the storage chains that we're seeing is mostly soil moisture. And so most of them do not have groundwater either. So, and they don't have human water use. So I think one of the reasons that they underestimate depletion in places like the Central Valley and stuff is because they don't have human water use. But you can see from the global hydrologic models that include human water use that their algorithms, their global algorithms, overestimate, either do not correctly get the source of water that's being used, or overestimate the groundwater use because we're seeing much greater depletion stores than we see from GRACE or from other regional models or from groundwater level monitoring data. So we try to work with all of the people that develop these models to make sure that we're not missing something, and so they just indicate that these are uncertainties, and when you're doing these large-scale models, I think. So I think in the future they will be trying to add human water use into the land surface models, and they have been trying to add irrigation and stuff, so they will be trying to add pumpage and things like that in the future, so that might improve the models.
Interesting. So, yeah, no, that's very helpful in terms of understanding some of the limitations. It sounds like that explains some of the lack of decline, but I'm wondering about the fact that the land models also just have less variability overall. Is that just because they don't have as large of a storage reservoir because they're only looking at soil moisture?
Right, I think so, because some of the work that was done by Sean Swenson, when he basically reproduced the GRACE data and tried to figure out how much storage capacity he would need to do that. And so he was able to match GRACE water storage by varying the size of the storage compartment. So right now, most of those models have, 1 to 2 meter soil profile, at most maybe 3.5 meters. But in some cases, say for example in the Amazon, he had to have a soil moisture storage of 8 meters. So I think it could be an artifact of just having a limited storage capacity. And others, like the global hydrologic models in Australia, where there's no human water use, they inverted to figure out what soil moisture storage change they would need to reproduce the GRACE data. So I think we'll be able to incorporate GRACE data in data simulation to improve the models in the future, and people are already doing that to some extent.
Thanks.
Hey, Bridget, it's Bayani.
Hi, Bayani.
Thanks for a great talk and great work again. So I think what I tend to get out of this, and you know, we've a lot of people have worked on global scale models, and I like to remind people when you do these things, you're really looking at the world with beer goggles, right? You have a fuzzy picture of what the world might look like, and the problem is when it's applied locally, right? And when you're looking at a problem locally, use a microscope, right? You don't use beer goggles. And so is that, I guess, safe to say, based on all you've done and the work you've done, it's really, if you have a local problem, then don't mess around with these large scale models, right? What you're saying even is if you just don't get a river correct, then even when you're using something for conjunctive water use and you don't have the right resolution to represent stream flow and depletion from that stream flow due to a well that's, you know, a couple 100 meters away, or a bunch of wells even, then you're not going to get it right, or you're likely going to get answers, but you don't really know why you're right or wrong. Is that fair statement, you think, from your experience now?
Well, you know, so there's so much interest in global modeling and to get a global budgets and stuff. But I mean, those global budgets are accumulation of all these small scale models. So when we did comparisons in the past between global models and GRACE to estimate sea level change, I mean, the global models were in the opposite direction. So it's not just, you know, and then also from this study, the local models may be off too. I mean, the Mississippi embayment model does not, you know, differ substantially from the GRACE, and suggests that maybe the regional model is underestimating capture from the streams in Mississippi.
I guess what I'm saying is the regional model already too coarse in a way that it can't represent, not necessarily heterogeneity, that's always a problem, right? But maybe it is not representing water tables near the rivers correctly. Right, and
right.
against there and losses and gains, you know, in specific areas. But they're very different to say, you know, here in Texas, where the groundwater conservation districts have a very aquifer specific model, which you worked on too, right? You know, a few decades ago, or 20 years ago, maybe. I know you were involved, but it seems like that's really, you can't get away from that scale.
Well, I think, you know, another point, Bayani, is it's nice to look at a lot of different things at a lot of different scales, and sometimes we can get insights from these comparisons. Mm-hmm. I mean, you know, we really didn't think that the Mississippi embayment had a problem before we started comparing with GRACE. You know, we had no, and maybe GRACE is wrong, but I don't think so. I mean, it's well within the uncertainty envelope of the GRACE solutions. So I think it's important to consider, to have an open mind and look at a variety of different things. And then, you know, I showed the study that Petra Dahl did, you know, looking at surface water recharging groundwater from the global model. So, you know, it can provide conceptual understanding sometimes, even if, but I think global models are not necessarily good at large scale either, because it's just basically summing up all the small scales. So when we looked at the global sea level, it didn't do a good job, you know. So, but I mean, I still think it's valuable maybe to do those global analysis, because you kind of get an idea of hotspots and stuff like that. And then the next step would be to go with a more regional and more detailed model to evaluate it better. So not saying ditch anything, but don't always emphasize global maps and global analysis, and that there's room for very detailed local studies. I mean, you see in the publication literature, you know, is this study too local, or is this too, and I would say the same thing, is this study too global, you know? So we need to look at a variety of different things to help with understanding.
Well, thank you.
And thanks for having your class attend. I probably would have nobody online if it weren't for that. So appreciate it.
Right. Yeah, a few people attended, but there's a lot of others.
So thanks very much. I know people are very busy and everything, so I presume. Appreciate the opportunity, and if anybody has any questions, don't hesitate to get in touch. And I hope you were able to learn something from this work.
All right, thank you so much, Dr. Scanlon, and thanks to everyone who joined us, and see you all next week. Have a great weekend.